Welcome back, folks, to another AP Chemistry video. Our focus for today is going to be on 1.3, which is the elemental composition of pure substances. So what we're going to do today is we are going to look and get a better understanding of how pure substances, that is elements and compounds, are produced and understand how they are put together in certain whole number ratios that give us a better idea of calculations of things like empirical formula, molecular formula, and just a general understanding of how compounds are put together as a result of this. So quite a few things we want to get to today. I'm very excited to be here as always. So thank you very much for listening, and we will just go ahead and get started, I guess. So our big learning objectives for today are understanding that chemical formulas have the ability to identify substances based on their unique combination of atoms. So different combinations of atoms result in different chemical compounds with varying chemical properties. Some pure substances are composed of individual molecules. These are known as molecular compounds, while others consist of atoms or ions that are held together in a fixed proportion, as described by what is known as a formula unit. So sodium chloride is an excellent example of this. This is an ionic compound with the chemical formula NaCl, so you would think there's just two ions that are present in the formula of sodium chloride. That is one of Na plus and one of Cl minus. However, that is not the case because ionic compounds form very large crystal lattice structures with repeating positive and negative ions. So what you find is that the chemical formula for these is just given in the lowest whole number ratio. According to the law of definite proportions, the ratio of the masses of the constituent elements in any pure sample of the compound is always the same. That is, sodium chloride is always going to be composed of, at least of the ratio, one sodium ion and one chloride ion. And the chemical formula that lists the lowest whole number ratio of the atoms is known as the empirical formula. So we're going to spend a little bit of time looking at empirical formulas, going through it and calculating them throughout the course of this lesson. So let's talk about varieties and different forms of matter. Matter comes in a variety of different forms, shapes, and sizes. So talk a little about elements. Elements are just simply the elements and things that are found on the periodic table. So if I whip out a periodic table, I find that there's 118 elements that are present on there. And each individual element that is present on the periodic table has its own unique chemical and physical properties that are associated with it. Each element on the periodic table, that is, if I were to look at a sample of nitrogen, for example, all of the atoms of nitrogen are going to contain the same number of protons. That is the distinguishing characteristic between different elements that are on the periodic table is the number of protons that are present in them. So all nitrogen atoms will have 7 protons. All oxygen atoms will have 8 protons, fluorine, 9 protons, etc. Now we can distinguish different isotopes, that is, of samples of the same element. That is, they will have the same number of protons but differ in the number of neutrons. So if I take a look on the right-hand side here, I find that oxygen has 3 different isotopes here on the right-hand side. Now all 3 of them have 8 protons. However, oxygen 16 has 8 neutrons. Remember that that is the mass number, 16 that is, which is the number of protons plus neutrons that are found in the individual isotope. You also see oxygen there with a mass number of 17, indicating that it has 8 protons and 9 neutrons, and oxygen 18 with 8 protons and 10 neutrons. So we've already discussed a little bit about isotopes when we did average atomic mass, but really wanted to break it down for you here. And then lastly, elements can exist as ions, where they have the same number of protons but differ in the number of electrons. Remember that electrons indicate the charge that's present on the atom. This is a periodic trend that for the most part is based off of the location of the elements that are on the periodic table. We'll get more into that when we do a little bit with properties of ionic compounds and things like that. But if you really want to understand more about ions, check out one of the nomenclature videos on this channel here. Matter can also exist as compounds. Now these are made up of multiple elements that are in a fixed whole number ratio. So for example, water is always H2O. That is, water is always 2 parts hydrogen and 1 part oxygen. It will always be that way. If the ratio of hydrogen and oxygen were different, then it would no longer be considered water and would no longer be considered H2O. Same with methane on the right-hand side here. Methane consists of 1 part carbon and 4 parts hydrogen. So it will always be the case if we were consistent of, or if we consisted of different elements in different whole number ratios, we would be considered a different chemical compound. And then lastly, NaCl here is always fixed with 1 Na and 1 Cl. We talked a little bit about formula units already. It is the smallest fundamental unit of an ionic compound. Ionic compounds are giant structures. They're made up of a lattice of ions of positive and negative charge associated with them. But what we do is we reduce that to the lowest whole number ratio. In this case, 1 sodium and 1 chloride results in sodium chloride. So that's why NaCl is the formula unit. Now, given some experimental data, and this is what we're really going to focus on in this particular part of the unit, we are going to focus on the fact that with that data, we can determine that fixed whole number ratio of atoms in a compound that is known as the empirical formula. And to do this, we're going to have to do a little bit of math, but it's not very complicated math to go through and do. Most of the time when you go through and do this, you're going to be given percentages. And when you're given percentages, it's pretty straightforward. You just need to do the following. Step number 1 would be to assume that the percentages are grams. So for example, if something had, let's say 27% carbon associated with it, you would assume that that is 27 grams of carbon. The next step would be to convert that gram number into moles, utilizing the molar mass that is found on the periodic table. One key thing to keep in mind here is that because we are looking at the individual atoms within a compound, we're not focusing on things that are diatomic. So if you're converting, let's say, grams of hydrogen to moles, in this case, we would use the molar mass of hydrogen that's just based off of the periodic table, 1.01, as opposed to a diatomic molar mass of H2, where it would be 2.02. Once that's done, we're going to divide each mole number by the smallest mole number that's present. So for each individual element within the compound, get the percentages to grams, convert them to moles, and whichever mole number is the smallest, you divide all of the mole numbers by that number. If all of the mole numbers, once you've divided them all, are whole numbers, they are your subscripts for the element in the compound. Nicely done. If they're not whole numbers, we have to multiply each by a whole number to get a whole number. So it's a little bit trickier when we start having to do some multiplication. There's really not a lot of that on the AP exam, mostly focused on just the basic empirical formula calculation. So as long as you can do that, you should be in really good shape moving forward. So just keep these steps in mind as you go through and try to solve for the empirical formula of a compound. So if we take a look at the problem here, it says that a compound contains 30% sulfur and 70% fluorine by mass, and it asks us to determine the empirical formula of the compound. So let's just follow each individual step as discussed previously. He's read this time. 30% sulfur, 70% fluorine. So remember, we assume that our percentages are grams, so we're going to start with 30 grams of sulfur and 70 grams of fluorine. All right, off to a good start there. The next step is to convert those grams into moles. So remember, we're going to utilize the molar mass that's present on the periodic table. So you're going to need to do a little bit of math. Thankfully, the College Board allows that now. So 19 grams for every 1 mole. And we're just going to plug those into our calculator and get our mole numbers. So take 30. These are all with decimal points. Want to make sure we keep things in the correct number of significant figures as we go through and do our calculations. Sig figs, albeit my chemistry students don't necessarily agree with me, sig figs are kind of a big deal. So this is going to be 0.94 moles. We're going to take 70 and we're going to divide that by 19. And we end up with 3.68 moles. All right, 3.68 moles. The next step is to divide by the smallest mole number. So we're going to divide each of these by 0.94. So that number is going to be 1. And we end up with a mole number of around 3.9. So a good rule of thumb is that if you are within a tenth of a whole number, we can consider that to be rounded to the whole number. Sometimes these numbers get rounded a little bit. We end up with some strange numbers here. Most of the time when you do empirical formula calculations, you're going to have a number that's much, much closer to the actual whole number here. But this is a safe bet that we can utilize this as a whole number here. So my empirical formula here is going to be SF4. Okay? So again, if we didn't get whole numbers here, we'd have to multiply by whole numbers to get whole numbers. I do have another video over empirical formula that will help you with that, but in the grand scheme of things, this should really take care of the situation here, all right? Okay, let's move on to the next topic. So another way we can utilize the empirical formula calculation is by looking at what are called hydrated compounds, and hydrated compounds are just that. They contain molecules of water. That's what it means to be hydrated, right? Empirical formulas of hydrates can be calculated the same way as other empirical formulas. What we do is we just treat the anhydrous compound and the water as if they are separate individual elements within the compound. So for example here, I would do the same work with the empirical formula calculation. I would just consider, rather than, let's say, S and F as separate entities, I would consider CaSO4 and H2O as separate entities. So you do the empirical formula calculations in a very similar way. You just focus on the anhydrous compound, that is the chemical formula before the water, and the water as separate entities as you do the empirical formula calculation. So you would determine the grams of calcium sulfate and then the grams of water, and then convert both those to moles and divide by the smallest mole number. Again, keeping calcium sulfate and water separate from one another. We treat them as if they are individual elements. Now for error analysis that are associated with labs with this, there are some labs that require a hydrated compound to be heated until the water of the compound has evaporated, usually using a Bunsen burner in a crucible. So we would take the hydrated compound and we would put it in a crucible, and then we would heat it, and heating it would evaporate the water out of the compound, leaving behind the anhydrous compound, or the compound that is without the water. And what we do with this information is then the difference between the mass of the original compound and the anhydrous compound is the amount of water lost. So if I look at the information here, I have the mass of the empty container and initial mass of sample and the container. So I can get the initial mass of the sample from that if I were to just subtract the initial mass of sample and container from the mass of the empty container there. So subtract the very first two components of the data table there, and you will get the mass of the hydrated compound. Notice what the student does here. They heat it once, get a measurement. They heat it again, get another measurement, and notice that there is a difference between the two. What that tells us is that there may still be some excess water within the compound. So it's very important when you do the empirical formula of a hydrate that you heat it to a constant mass. Once I have the sample and the container after the third heating, I can actually subtract that from the mass of the sample in the container, and that will give me the mass of the water that is lost. I can then utilize that information and the mass of the anhydrous compound. From that information, I can calculate the empirical formula of the compound. So what you need, again, is the mass of the compound without the water and the mass of the water that has evolved from the reaction. So take a look at the data table and get a really good, clean understanding of how that's going to look as you go through and do these empirical formula calculations. Figure out, how can I get the mass of the water from that information in the data table, and how can I get the mass of the compound without the water? Once you have both of those numbers, then you just perform an empirical formula calculation with the anhydrous compound in the water to determine the empirical formula of the hydrated compound. So what are some possible sources of error that are associated with this? Well, let's say we heat up this system here and some of the compound splatters out. Well, splattering chemicals would result in error with increased assumption. I think assumption is probably the word there, water being lost, because what we're doing is we're subtracting the mass of the hydrated compound from once it's been heated. And so if some of the anhydrous compound leaves, well, that would result in the mass or subtraction being greater than what we would expect it to be. So we would assume that that's water being lost. So the mass of the water would be increased, and thus the empirical formula of the hydrate would be miscalculated. Not heating the compound to a constant mass would result in a decrease in the water lost, as unboiled water is left in the compound. So when we would subtract those two, we'd get a value that is smaller than what would be expected. And so we would assume that the mass of the water being released is lost because there's still some water left in the anhydrous compound, which would result in an increased mass of the anhydrous compound. So we need to take into consideration what are some possible sources of error as we go through and do the mathematical calculation with this. So I'm going to go ahead and move forward with some of these calculations. So we're given a little bit of a free response question we want to take a look at here. It says in the first two experiments, a student is assigned the task of determining the number of moles of water in 1 mole of MgCl2 and NH2O. So eventually what we're going to need to do here is figure out this number here, this N, this mole number in front of the hydrated compound. First question asks, explain why the student can correctly conclude that the hydrate was heated a sufficient number of times in the experiment. And so if I look at the data here, remember what we talked about. The student had an initial sample in the container and then heated it and noticed that quite a bit of mass was lost. The student heated it a second time and noticed there was more mass that is lost. The goal here is to heat until we have a consistent mass across the board. So I know I've heated this enough because after the third heating, the mass did not change. Thus, all the water is boiled off. All right. So I know it's a bit harder to read, but and normally you would want to expand upon this as a free response style question. I'll post a video eventually about how to go through and answer and respond to free response questions, but you get the idea here. After the third heating, the mass didn't change. And so that tells us that all the water has been evolved out of the anhydrous compound, and I'm ready to go do my empirical formula calculation. All right, let's move on to the next one. All right, so let's go ahead and take a look at part B of this practice problem. So we're given the same set of information, but what we need to do with this is to determine the coefficient of N for H2O. So again, we're going to be working on calculating the empirical formula of that hydrate. Now, in order to do this, we're going to need a couple of pieces of information. I'm going to need essentially, well, 3 pieces of information. I need to know the mass of the original compound. Okay. I need to know the anhydrous mass, that is without water, and I need to know the mass of the water in and of itself. Once I get these last 2 pieces of information, I can then utilize that to be able to calculate the empirical formula of the hydrate. So let's look at the information that's given to us in the problem here. I can get the mass of the initial sample by simply subtracting the mass of the initial sample in the container and subtract the mass of the empty container from that. So to start this off, I'm going to take 25.825 grams. And I'm going to subtract from that 22.347 grams. And then let's see what we get from that information. So plug that into our calculators. Little ASMR calculator for you today. I end up with 3.478 grams. Okay, and again, that is of my total compound. So we're going to hold on to that piece of information here. The next piece of information I can get from this is actually the mass of the water from the reaction. So if I go and take a look at this, the student heated this thing 3 times. We have the initial mass of the sample in the container and the mass of the sample after the heating. So if I subtract these 2 values, I will get the mass of the water that evolved from the reaction itself. So I'm going to start off with 25.825 grams and subtract from that 23.977 grams. All right, so we're going to subtract those 2 values. Once again, plug those into our calculator. And I end up with a mass of 1.848 grams. Okay, so that's the mass of the water that is evolved. So the last thing I want to do here is I'm actually going to subtract these values because the mass of the sample with the water minus the mass of the water will give me the mass of the sample without the water. So if I subtract 3.478 and 1.848, what I get is a mass of 1.630 grams of MgCl2. All right, now what I'm going to do is I'm going to utilize this information, these 2 masses here, and we're going to do an empirical formula calculation with them. So this is the key difference between regular empirical formula and empirical formula of a hydrate, is that we can utilize both of these numbers here as separate entities in our empirical formula calculation to solve for the number that's going to appear in front of the hydrate. All right, and let's rewrite this information up here at the top. So 1.630 grams of magnesium chloride and 1.848 grams of water. All right, get rid of these down here at the bottom. And now, like I said before, we treat this like an empirical formula calculation. So grams to moles, divide by the smallest mole number and see what we end up getting. So we're going to need the molar masses of these compounds. I know this is 18.02. Magnesium chloride I do not know off the top of my head. So 35.45 times 2. We're going to add to that the molar mass of magnesium. 94.31. End up with 95.21. Let's get these mole numbers calculated. So I end up with 0.01712 moles. And with water, 0.1026 moles. Again, once we get our mole number, we divide by the smallest mole number, which is going to be that of the magnesium chloride, so 0.01712. So that's going to be 1. And I get 5.99, definitely close enough to call that 6. So all it's asking for is the coefficient of n. That is going to be what that is, because that is the number that is going to appear in front of water, all right? So again, it evolves itself from a simple empirical formula calculation. We just need to make sure that we make the anhydrous compound, that is the magnesium chloride, and the water 2 separate entities, and then we can go through and do the calculation accordingly, all right? Let's take a look. I think we have one more problem associated with this bit of information. So a student heats the hydrate in a crucible that is uncovered, and some of the solid splatters out of the crucible. This splattering will have what effect on the calculated mass of water lost by the hydrate, and to justify your answer. So again, with these justify your answers, I'm probably not going to justify them fully with my writing, but rather probably with the verbal information I'm going to provide for you, simply because I just don't have the space and my handwriting is terrible. So if we take a look at this information, some solid splatters out of the crucible. So what I can expect from that information is that this numerical value here, the sample in the container after the third heating, is going to be lower than what I would expect, right? If some of the solid splashes out of the crucible, that means that the final mass is going to be lower than what I anticipate. Remember that we utilize this number and the initial mass of sample and container to determine the mass of the water. So if I'm subtracting a number here that is smaller, then I can anticipate that the mass of the water that is calculated is going to be higher than what I would expect, okay? And again, that has to do with the fact of what you are subtracting when you go through and determine the mass of the water as you calculate the empirical formula of the hydrate, okay? So again, I'm not going to fully justify the answer based on my writing. I'll post another video that shows what types of writing styles and techniques you want to utilize as you go through and justify your answer in regards to writing for an AP exam and those types of things. But again, just a little bit of simple math here, just thinking about what the answer to the problem might be and what would happen if I were to do some calculation. Again, error analysis is very important for the College Board and very important for science in general. So just make sure that you're practicing going through and doing some error analysis practice. Very, very important, all right? We'll see you in the next slide. So the very last type of calculation we're going to do in this particular unit is what is known as a combustion analysis style problem. And this is an analytical technique used to determine the empirical formula of a hydrocarbon. Now, hydrocarbons are, well, just what you think that they would be. They contain carbon and hydrogen. If you recall back from your original Chem 1 experience, you probably remember that combustion reactions always end up producing carbon dioxide and water as a product of those reactions. So when we go through and look at a combustion reaction in and of itself, we can actually make a couple of assumptions based on that information. First is that all of the carbon in the hydrocarbon is going to be converted into CO2, and all the hydrogen will be converted into water that is produced from the reaction. So if we can actually experimentally figure out how much CO2 we have and how much water we have from a combustion reaction in terms of grams, I can then figure out how many grams of carbon I have in CO2 and how many grams of water I have, grams of hydrogen I have in water, and then utilize that information to figure out what the empirical formula of the hydrocarbon was. So again, based on the information provided, we can determine grams of carbon and grams of hydrogen in the hydrocarbon. Carbon is going to be determined by finding the grams of carbon in CO2, and hydrogen will be determined by finding the grams of hydrogen in water. So once we achieve the gram numbers, we treat this like a normal empirical formula style problem. If we have more than just carbon and hydrogen in the hydrocarbon, we have to go to grams. So it's kind of a little bit of a shortcut here. If we just have carbon and hydrogen in it, we can stop at moles if we wish to do so. So that's probably what we're going to end up doing because the hydrocarbon question I have is just based off of carbon and hydrogen. Now, occasionally, like I said, you will encounter more than carbon and hydrogen. You have to go to grams. And then what you'll probably end up having to do is to subtract those values from the mass of the hydrocarbon originally in order to determine the mass of any other element that is present in the hydrocarbon. I'm just going to do carbon and hydrogen because that's kind of the limit of what we normally do with AP style problems, at least at this point in time. If I see something that pops up later, I'll revise the video. So the very last problem we're going to do here is to determine the formula of a hydrocarbon if 7.2 grams of water and 14.1 grams of carbon dioxide are produced from that reaction. So I'm going to start off by determining how many grams of hydrogen and how many grams of carbon are present in each of these two materials here. So I'm going to start off with carbon. So 14.1 grams of CO2. All right, in order to do this, we need to get grams to moles. So 44.01. After a while, you do enough of these, you just kind of memorize some of the more common molar masses. And then what I can do here is say that 1 mole of CO2 is equivalent to that of 1 mole of carbon. Remember, we can go from compound to element within the compound if we look at the subscript that's present. There's 1 carbon in CO2, so I can do a 1-to-1 mole ratio from that. And then we're lastly going to do water, so 7.2 grams of water, right? Grams to moles. And then remember, because water has 2 moles of hydrogen per H2O, we're going to do a 1-to-2 ratio. All right, now what we're going to do is we're just going to calculate those mole values and then just move forward like a normal empirical formula calculation. The only benefit to this is that I didn't go to grams, don't need to here, because if I did that, I would just end up having to go back to moles again. So I'm kind of skipping a step here, which is perfectly fine. All right, so 0.320 moles of carbon. 7.2, I have 18.02. And we end up with 0.799 moles of hydrogen. Okay, off to an awesome start. Now the last part here, divide by the smallest mole number, and let's see what we get. So we're going to divide both of these by 0.320. So this is going to be 1. And this is actually going to be, it says 2.49, we're around that to 2.5, okay? So what we end up here is a situation that does not end with our empirical formula being whole numbers, okay? So we have 1 and 2.5. So for carbon, we're given 1, and for hydrogen, we're given 2.5. So the very last step of the empirical formula calculation was that if we do not have whole numbers, we multiply by a whole number to get a whole number. You can probably visualize this pretty well. 2.5, in order to multiply it to get to be a whole number, we need to multiply both of these by 2. So what we end up with is C2H5 as our empirical formula here, okay? Now, if you're having trouble visualizing that, here's what I would do. You see that 0.5 number here? Well, 0.5 as a fraction is 1 over 2, right? Whatever the denominator of that is, that's what you're going to multiply by. So if this were, let's say, 0.33 or 0.66, those are fractions of thirds, right? So you would multiply by 3. So figuring out the fraction that this decimal would be in is one way you can determine what number you're going to end up multiplying by in order to figure out the empirical formula, all right? So it does take a little bit of time, a little bit of practice, but overall, like I said, as long as you are strong with your math and you're strong with your empirical formula calculations, you should have no problem with doing any form of combustion analysis. All right, folks, that's going to wrap it up for me today. Hopefully you found this video very useful in calculating and learning empirical formulas. If you have any questions, just let me know. And as always, thank you for taking the time out of your day and spending it with me. And I will be posting some more videos here soon. Take care, everybody. Have a great day, and we will see you soon.